talk about the state of the universe. So in 2017, we know several things about the universe, so we're going to go through this briefly this evening or morning, depending on where you're at. One, very fundamental that we've known since 1929, the universe is expanding. The universe is 13.8 billion years old. The universe is very close to being geometrically flat. And the universe is composed approximately 69% dark energy, 26% dark matter, 5% atoms made up of mainly hydrogen, some helium, and a little bit of everything else, a tiny fraction of neutrinos, and even a smaller fraction of photons. Now, I'm going to talk a little bit about how we know all of that, and that's really the nature of the talk. So, if we go through and hopefully we think about measuring distances, we measure distances in the universe by how things appear. The further away something is, the fainter it appears, like the candles in this diagram. We can't just measure things directly in the universe, and so one of the principal ways that we measure distances in the universe is by looking at how bright astronomical objects appear, making some assumptions about them, and then making some conclusions, sometimes erroneous, but normally rather useful. The other thing that we can measure is redshift. Now, redshift can be caused by a number of things. It was originally thought of that redshift was simply a Doppler shift. So that, for example, if you measured a galaxy and you saw that its light was redshifted, that meant it was moving away from you. If it was blue shifted, it would be moving towards you, and you can calculate it directly by the amount of redshift. It turns out that if the universe is expanding, the expansion of space also redshifts the light of galaxies, but it doesn't blue shift it unless the universe is collapsing, which it is not, it's expanding. So when we see redshift, it's always a combination of a galaxy's motion, usually pretty small, plus the expansion of space. In 1929, Edwin Hubble went out and measured how bright stars were in nearby galaxies and used the redshift information from Vesto, Melvin, Slipher, and a couple of his own, it would appear, although it's not completely clear. Hubble was not great at referencing people clearly, I'm afraid. But you can imagine in this diagram across the bottom, from brighter stars to fainter stars, Hubble measured distances by essentially taking the square root of their brightnesses. And then he took how much they were redshifted, and he saw that the further an object was away, that is, the fainter its stars, the higher its redshift, the faster its redshift. And from that, he announced that the universe was expanding. And you can understand that just by a simple cartoon. Here is a universe which I'm going to expand. And when I expand it and I overlay the before and after, you see the following diagram. You see that nearby objects haven't moved much, and distant objects, well, they moved a lot. If I was measuring their redshift, these distant objects will have large redshifts. So you get this further away you are, the more the redshift in expanding universe. And it really doesn't matter where you are. Now, imagine a universe is expanding. Well, let's run it in reverse and think what happens. When we run the universe in reverse, we can look back to a time when things are on top of each other, and it naturally brings you to the idea of a Big Bang. A time in the past where the expansion of the universe, run backwards, places everything in a single point at a single time, or a single place at a single time. Not necessarily a point, unless it's everything we can see. Now, what the Big Bang is, unclear. We have ideas that the Big Bang was something related perhaps to the juncture of quantum mechanics, quantum field theory, and gravity. We have the idea of inflation, that I'm not going to talk too much about today, or the idea that the universe went from the size of literally an atom to the size of the visible universe very quickly. So we only know what came after the Big Bang. And the best image we have of the early universe is the cosmic microwave background, which I showed you here. This is an image of the entire sky where we can see hot and cold spots. The universe there is about 2.73 degrees Kelvin. And the hot spots here and the cool spots here are roughly 1 part in 100,000 different from each other. But these hot and cold spots are dense and underdense parts of the universe, and are the parts of the universe that eventually become clusters of galaxies. We'll talk more about those spots later on in the talk, but that image is an image that is the furthest thing we can see in electromagnetic radiation. But it's also, as you will see, a very powerful place to measure and understand the universe. I believe David Spergel talked to you a fair bit, but I'll review it. Now, imagine I have an expanding universe. If I want to think of it just from a simple graph, then the universe gets bigger. That means galaxies right now have a certain separation at a certain time. And when I run the universe in reverse, of course, I land them back to a time when those two galaxies are right on top of each other. And so the slope of that line, based on two galaxies separation right now, tells you when the Big Bang is. That is, if I can measure the slope of that line, which turns out is the expansion rate of the universe, distance divided by redshift, then I can estimate the age of the universe. Life isn't quite so simple, unfortunately, because, well, let me tell you before I go there, just to say that for my PhD thesis, that is what I did, is I measured how fast the universe was expanding in the local universe. Here I am in 1993 with my PhD supervisor, Robert Kirshner, showing him the result of just under 4 years worth of work, and my value for the Hubble constant turned out to be that the Hubble constant was roughly 70 kilometers per second per megaparsec, or, drawing that straight line back, an age of the universe of roughly 14 billion years. Now, it turns out subsequent measurement has sort of converged on that answer. Doesn't mean I was there first or anything, far from it. I was part of the consensus that led to the current adoption that the Hubble constant is around 70 kilometers per second per megaparsec. The universe is roughly 14 billion years old. All right, now, if you're going to make observations, if you want to understand them, you need to have a theory. And the theory that we base essentially all cosmology around is Einstein's theory of gravity. In 1907, Einstein had a revelation when he saw, of all things, someone falling off a roof. And he thought, I think that person doesn't feel gravity as they fall. Rather, that the acceleration due to falling is exactly offset by the force of gravity. That's probably not what most people would think of when someone was falling off a roof, but that was Einstein's great thought. And from that single idea, to reconcile that acceleration due to moving faster and acceleration due to gravity were always equivalent, he had to work for nearly 8 long years, more than 8 long years. And so the idea that you can't tell if you're in a rocket ship or on planet Earth is a very profound part of Einstein's theory of gravity. And to reconcile that idea that these two things were always equivalent, Einstein had to develop the field equations of general relativity, which ended up telling us that space is curved. Now, it was the publishing of this theory and the subsequent observational support for it, from the idea that stars were displaced around the sun during an eclipse compared to when the sun was not there due to the bending of space. Well, that was his great prediction. It was seen to be true, and that is the thing that made Einstein famous around the world. Not E equals mc squared. That made him famous in physics. This is what made him a science superstar. Something that's quite forgotten now, as the average person, when they think of Einstein, thinks of E equals mc squared. It's a little easier to explain, I'm afraid, than the field equations of general relativity. Now, astronomers vindicated Einstein's theory of gravity by going out, as I said, and looking at the displacement of stars near the sun during an eclipse compared to the sky when the sun was not there. And these observations agreed exactly with the theory within the experimental error. The first experiment was not very good. It was done in 1919. Subsequent experiment in 1922 here in Australia by American astronomers was much more precise, and I show you the data there. Here's the data to show you why it wasn't very good in 1919. On the left, images made by the Astronomer Royal by Eddington were through clouds. Images on the right taken by the Astronomer Royal were out of focus. The ones on the right are the ones that were used to do the experiment. After general relativity was published, cosmology was a natural place to use it almost immediately. And the first person to do anything was De Sitter in Holland. And he did the simplest thing possible, an empty universe. And already that empty universe showed the idea of things like redshift. Now, Einstein was quite critical of De Sitter, although in the right picture, he's there discussing with De Sitter some of his equations, because he thought that an empty universe was ridiculous. Einstein and De Sitter went on later to do a very famous solution to his equations, but Friedmann, and then later Lamont, went through and calculated universes that were homogeneous and how they would behave. And these are the set of equations that we still use to this day. On the left, you see Lamont, a Belgian monk. On the bottom, you see Alexander Friedmann, St. Peter's, who unfortunately died at a very young age soon after he published his equations. So, Friedmann, and rederived again by Lamont, created what we call the Standard Model. A universe that assumes, it's a set of calculations that assumes the universe is isotropic, that means it has no preferred direction, and homogeneous. This turns out it makes the equations of general relativity, which are equivalent to 11 nonlinear partial differential equations that have to be simultaneously solved, and it knocks it down to 2 equations, which are ordinary differential equations, and can be solved. This is the main ordinary differential equation. It's quite simple, and there's a few things there. You see the speed of light, c. You see the gravitational constant, g. Of course, pi is just the numeric constant. A is the scale factor. It tracks the size of a piece of the universe, and one can measure it. So it essentially tells you how long, or how big a piece of space is over time. And because photons, light, is redshifted by the expansion of the universe, if you can measure how much light is shifted, you can measure very accurately the relative size of the scale factor A at any given time. We can actually measure that to about 1 part in a million. quite easily now. K, I have mentioned, is geometry. It takes a value of +1 if the geometry of the universe is closed, -1 if the geometry of the universe is open, and 0 if it's flat. Now I'm going to explain what that means. So I'll explain what that means in just a second. The parameters that we astronomers talk about are the Hubble parameter, which is how much the scale factor changes compared to its value. So that is the fractional change of the scale parameter of the universe, or the size of the universe. And it turns out that is the Hubble constant right now. It's not constant, but it has a value now. That's what we call the Hubble constant. And it's, as I said, the reciprocal of it is about 14 billion years. In that set of equations, there's the notion of critical density. Critical density is where the geometry of the universe is flat. It's not closed, spherical, and finite. It's not open, infinite, and hyperbolic. It is at the critical juncture, the dividing line between the two geometries. It turns out you can calculate that in forms of the Hubble constant and these other constants, and it has a value for the Hubble constant equals 70 of 9.2 times 10 to the minus 27 kilograms per meter cubed. That's a very small number. That's 30 orders of magnitude less dense than the Earth. Finally, we use the notion of the density parameter omega, which is the ratio of the density of the universe now compared to that critical density. Now, I'm going to show you later on that we think omega is very close to 1, but that the average density is near 9.2 times 10 to the minus 27 kilograms per meter cubed, which tells you that Earth is a very unusual place in the universe. Now, I should say the density made up in that value row can be any form of matter or energy. It could be atoms, it could be photons, it could be neutrinos, it could be something which we'll talk about known as the cosmological constant. Anything that has energy can be converted back and forth to mass. So under Friedmann's law, you get an interesting set of possibilities. If the universe is absolutely empty, then the universe expands uniformly over time and keeps on getting bigger and bigger over time. This universe has less than the critical density and therefore has hyperbolic geometry, which means it extends forever in time and, as you can see in this graph, space. If the universe has less than the critical density, but is not empty, then the universe slows down if that density is in the form of atoms or other things that gravitate like atoms do. And so you get a trajectory where the universe slows down, the universe is not quite as old as you might think from the Hubble constant, just simply extrapolated, and the universe keeps on expanding forever, but keeps slowing down over time. Asymptotically, ends up coasting at the very end. And finally, you have a universe which has, in normal matter, greater than the critical density, or omega matter is greater than 1. This is a universe which turns out to be about 2/3 as old as you would think from just extrapolating on the straight line. And it's a universe that will eventually stop expanding, go in reverse, and collapse. So all these universes start with the Big Bang, but only the omega matter greater than 1 universe ends in what I like to call the Ganapkian, or the Big Bang backwards. All right, let's talk about geometry. If the universe is flat, triangles add up to 180 degrees and all is normal. The universe extends well beyond this grid I show you in all directions to infinity. But imagine if the universe is finite or infinite, it can have different shapes. In these different universes, triangles add up to different angles. So an infinite light universe, triangles add up to less than 180 degrees. In the finite heavy universe, spherical, then the universe and the angles of triangles add up to more than 180 degrees. All right, so in 1994, I had just finished my PhD. I was trying to figure out what to do next. And an opportunity came to go out and to measure the universe's past and do a fundamental experiment on the universe. That is, imagine I measure how fast the universe is expanding right now, and I measure how fast the universe is expanding in the past. That is, if I can measure the Hubble constant for nearby objects and then very distant objects, I can see how it changes. If I see no change over time, well, that means the universe is coasting, and that's equivalent to essentially being very nearly empty compared to the critical density. On the other hand, there is a line where the dividing line, that is the critical density of the universe in normal matter, where gravity wins on one side of the line and gravity loses on the other side. That is, if the universe expands, is slowing down faster than that yellow line, gravity will win, and I know the universe is therefore finite and has closed or spherical geometry. The other side of that yellow line, gravity loses, and the universe will expand forever. It is infinite in both time and space because it doesn't have enough density to slow down. How do we do an experiment? Well, you need something bright, and nature provided us type 1a supernovae. Now, type 1a supernovae can occur when two stars in a binary are able to interact with each other. The more massive of the two stars, as it evolves, will puff up and can donate its material to the less massive of the two stars, making the less massive star the more massive of the two stars. In the center of the first star, you end up with a white dwarf star, the remnant that our sun will eventually become. White dwarf stars are what we would say is electron-degenerate balls of gas. They're very small, about the size of the Earth, but there's a solar mass there. Now, as the second star, the big heavy one now, evolves, it will puff up and it will start donating material to the white dwarf. And that white dwarf becomes gravitationally unstable at 1.38 times the mass of our sun. Actually, 1.383 times the mass of our sun. And it will, because of that instability, start to burn very rapidly its nuclear fuel in the form of carbon and oxygen, and the whole thing will go up in a period after about 1,000 years of simmering, in a period of a second, as a giant thermonuclear bomb. These things end up glowing 5 billion times brighter than our sun, take 20 days to reach maximum brightness, or maybe 17, and then fade away into oblivion. They produce 70% of all of the iron in the universe. Now, how did we learn to measure distances with these? That was a group I worked with in Chile, although they did the work before I started working with them in Chile. So, led by this group of individuals, they realized that you could measure the distances very accurately with supernovae by doing a 5-year experiment. I was, in 1994, visiting Chile, just before moving to Australia, and I met Nick Sunset, shown here on the right, who had been a leader of that Kharagpur survey in Chile, and we discussed using their new knowledge with some of the new other observational telescopes and instruments that existed to do this experiment. This happened in 1994. And what we were able to do was to use the new digital cameras. Can you hear it? Is everything okay? They could use the new digital cameras to go out and we could go out and take literally thousands of images in a night and see hundreds of thousands of galaxies. The images look like this one. We would have to sift through with software to find needles in the haystack of the night sky. So the supernova in this image, of which there were 4 this night, is contained in that box. And the way we could find it is we took 2 images separated in time, and those images as one of my principal jobs was to write software to go through, sift through about 50 gigabytes of data back in 1994 to find that things had changed. The reality is the software didn't work, but it worked well enough. So I'm going to skip the movie for time and say, after 3.5 years worth of hard work, here was what our data looked like. Here's the different trajectories we're expecting. Each supernova gives a measurement of the expansion rate. We go back all the way back to almost 8 billion years in the past, and you can see that the nearby objects, you can't really tell what's going on. These are those with that circle, but the distant objects, well, they are not in the bottom part of the diagram or in the yellow part of the diagram. Rather, on average, they're above the line in the part of the diagram where the universe was expanding slower in the past and had sped up. So that would indicate that the universe was not doing what we expected, that the universe was accelerating instead of slowing down. Now, that was quite a surprise to us at the time. We thought, geez, we must have made a mistake. We checked our work very carefully. We were competing with a group at Berkeley led by Saul Perlmutter, and it turns out at the same time they were scratching their heads because, of course, they were getting the same result. Neither of us knew of the other team's result. We arrived at it independently, and 2 papers came out in 1998 and 9 that talked about the evidence for an accelerating universe. And so it is for that our team won the Nobel Prize. Here we are together in Stockholm, 2011, and here Saul's team is there as well. So, what on earth would cause the universe to accelerate? Well, Einstein was there in 1917. He came up with the idea of the cosmological constant, energy that is part of space itself. If you add a form of energy into the Friedmann equations, then it turns out that energy as part of space makes gravity repulsive rather than attractive. It makes gravity push rather than pull. And so that is, even to this day, our best idea of what is causing the universe to accelerate. We often refer to as dark energy because we're not absolutely sure it's the cosmological constant, which never changes in the history of the universe. It is a fundamental part of space that does not change. Dark energy, we have not yet shown, doesn't change, so we're still continuing to try to understand it. The detailed analysis of our supernova results was that the universe needed to be about 30% gravitating matter, that's like things that we're made out of, atoms, and 70% stuff that we call dark energy, material that was pushing on the universe. In 1998, this was a very controversial measurement. I have to admit to not being completely sure about it myself because it seemed so crazy to me. I was pretty sure our observations were correct, but I was worried about the interpretation and that something was just missing. So groups went out around the world and started making measurements and trying to understand if this could be possibly right. Now it turns out in Friedmann's equation, as I told you, these are the various things if the universe is only made out of gravitating matter. But if the universe is gravitating matter and dark energy, you get a different family of trajectories. like the one in red that I've just shown you, where the universe initially is made up of gravitating matter, normal material like atoms, and as space expands, this material gets diluted over time. The cosmological constant, lambda, is part of space itself, and so it becomes more important over time compared to things like atoms. That changes the balance of the universe over time. So initially, the universe would be full of things like atoms. It would be slowing down. Then as the universe becomes bigger and bigger, the cosmological constant that is part of space itself doesn't change, and it eventually becomes the dominant part of the universe. And when it takes over, the universe starts to accelerate, and so you get this very funny-looking curve compared to what a universe that only had normal matter in it would have. So, one of the first experiments done that was precise was done here in Australia, and it was a map of gravity by looking at 221,000 galaxies. And so this experiment didn't have particular sensitivity to the cosmological constant, but it could measure very accurately omega matter. And it is done by making measurements, comparing them to simulations of gravity, where we essentially start the universe off and we allow gravity to take deviations from the cosmic microwave background and that we see there and to form structures in the universe. And so you essentially go through, create the universe in a computer, and then you compare the universe to what we actually see. And so here is that comparison made in 2001. The observed data is on the left. The simulated universes are on the right. And by your eye, hopefully you can see that model 2 is a little like the data. Model 3 is the one that looks most like the data. And model 3, it turns, is what the computer analysis says is the most likely the data. And that is a universe that is 30% of the amount of stuff to make the universe flat in omega matter. So that is an experiment done in 2001. So that experiment was quite precise, within probably 5%, but it once again showed an age-old problem. There was 6 times more gravity in the universe than we can account for in atoms alone. There is something like dark matter out there, material that we cannot see except for through its gravitation. So dark matter is another problem, not really shown by supernovae, but by this and other experiments that directly measure gravity. Dark matter is seen everywhere in the universe where we're able to measure it. And we think it could be some undiscovered particle that, like a neutrino, can pass right through Earth. A neutrino really is a form of dark matter since it seems to have mass. It has gravity. Dark matter has gravity, just like atoms, but is essentially invisible because it doesn't interact with anything. And we see it in clusters of galaxies and individual galaxies. Now, I told you about the cosmic microwave background earlier, and this turns out to be an incredibly useful laboratory in space. What we see here are sound waves that have been splashing around the universe since the time of the Big Bang. And of course, they have a scale which is equal to the speed of sound times the age of the universe, and that allows us to actually have a measurement very accurately of the expansion to this time in the universe, when the universe was about 380,000 years old. So, if you think about those waves, they also tell you what is in the universe, because just like a pond of material, if I throw a rock into a pond of honey, the splash marks are different than in a pond of water. The Big Bang was equivalent to throwing gravel into the universe. Those waves sloshed around, and then we have an image of them here, 380,000 years after the Big Bang, when the universe went from being ionized to recombined. And so we can compare those waves to essentially the splash marks expected for different things in the universe. So here is the way we measure those splash marks. We measure how many waves there are of different size. And the size scale essentially goes around the bottom. It's logarithmic. But if you get to these are modes in the universe, think of them as spherical harmonics, for those who know what those are. That scale at about L equal 200 is about a degree. So if the universe has different amounts of baryons, so that's atoms, you can see how the splash marks look different. If the universe has different amounts of dark matter in it, then the splash marks look different again. So by looking at the splash marks, we can tell the difference between dark matter and baryons. Here is what the data really looks like in splash marks. And that turns out to tell you very precisely that for every atom of mass in the universe, there is 6.5 times more dark matter. You get rid of the dark matter, and the curve doesn't fit what we've seen at all. These curves were predicted 15 years in advance of the measurements. When you can predict things in advance, you have a very good idea of what's going on in the universe. The other thing we can do is we can look at the splash marks and how big they look. Because remember, if the universe has different shapes, then triangles add up to different angles. That means the shape of a triangle is distorted, and that's equivalent of saying that the universe acts like a magnifying or demagnifying glass. It ends up, the whole universe acts as a lens. So if the universe is closed, that's like looking at a spoon in the back, and you're magnified. If the universe is empty, you're demagnified. Or if the universe is hyperbolic, open, you demagnify, and of course you're just right in the flat universe. So it turns out, again, that you can look at it in terms of the size of those splash marks. They depend very much on the curvature of the universe. They depend only a little bit, it turns out, on dark energy. And the little bit on dark energy is because if the universe accelerates, they're a little further away than they would be otherwise. So you can fit for all of these things simultaneously, and what you find out is the universe is exactly flat to within 0.5%. That means that the universe has critical density within 0.5%. Quite remarkable. So we put this all together. We know that everything in the universe adds up to 100% of the critical density. 30% of that is gravitationally attractive, and you're left with 70% mystery matter. That 70% mystery matter seems to be the same stuff that the supernovae have pointed to is accelerating the universe, dark energy. And indeed, with the current measurements, we can actually look and show that dark energy is by far and away the most consistent form of material at 70% of the universe with what we're seeing, not just with supernovae, but with the cosmic microwave background when you add other information. So we live in a very messy universe, a universe that is 95% dark energy and dark matter. Stuff whose gravitational effect we can see, but we don't really know what it is. Essentially, the invisible material. Only 5% of the universe are the atoms that we know and love and understand here on Earth. So, the density of the universe we know very accurately. It turns out that we're very close to critical density. The Hubble constant is very close to 70, it turns out. And so that is how much material there is in dark energy, dark matter, and atoms. the photon density. Turns out we know that very accurately because the cosmic microwave background is almost a perfect black body. It fills the universe, and so I can use a variant of the Stefan-Boltzmann law to calculate its energy density, and that is what it is in kilograms per meter cubed. It is roughly a 20,000th of the critical density. Neutrinos. Well, neutrinos seem to have mass, and it turns out we can get a sense of how massive the neutrinos are because they affect the structure of galaxies in the universe. And we have made very good measurements now, I haven't shown you them, of the structure of galaxies in the universe. It turns out that with the best measurements of how galaxies are distributed in the universe, they look more like the image on the right here than the one on the left. And the fact that we don't see any of the smearing on the left tells us that the total mass of neutrinos has to be less than 0.25 eV. If they had any more, then they would smear out. If they had a higher mass, they would have a higher density, and they would smear out the galaxy structures that we see today more than we actually do. The lower limit, 0.05 eV, comes from neutrino experiments here on Earth. So it seems to be in this area. It turns out that means they're not very important in the universe, but they're not completely negligible, which is interesting and slightly surprising. So the model that we have, the Standard Model of 2017, has not changed basically at all in the last 20 years. We had the universe born with density fluctuations left from the Big Bang. We normally think that they are caused by the inflation of quantum fluctuations. That is an idea that gives the right answer, but it is a bit of a cartoon. The universe is full of photons, neutrinos, baryons, dark matter, dark energy. The universe has to be highly homogeneous, 1 part in 100,000. General relativity works, it works really well. And all those things seem to be consistent with the universe and with essentially every measurement we make. The only little thing that's emerged is that Adam Rees, in 2016, has published his value of the Hubble constant, and that value of about 73 kilometers per second per megaparsec disagrees at 99.9% confidence with the Planck cosmic microwave measurement, the cosmic microwave background measurement, and so there's a discrepancy there. So it could be that there's something weird going on in the universe, and the expansion of the universe is not happening exactly as expected in our model, or it could be that there is an error at a few percent in the measure of Hubble constant, either nearby by Adam Rees's measurement, or something being wrong in the Planck measurement, which is a bit more accurate. So it's a great model, it fits everything we see, except for it requires inflation, something we have to make up, dark matter and dark energy, two other things we need to make up, but seem completely consistent with everything we know. So, the big questions. What is dark matter? What is dark energy? Why do neutrinos have mass? It turns out the beautiful equations that we have in quantum field theory would suggest, as they currently do, that neutrinos should have zero mass. Yet we're pretty sure they seem to have mass. The equations of quantum field theory and particle physics have photons in the early universe being annihilated or being created from the annihilation of all other forms of mass. And yet, for every atom, there are 10 to the 9 photons. So that tells you that there's some asymmetry in the equations, not yet understood, at 1 part in 10 to the 9. And finally, what is inflation? It's a cartoon where the universe blows up from a tiny size to at least 60 orders of magnitude, could be more, and we don't really understand why that would be. We can make sums up, but those are the outstanding questions. And so I will stop there as the State of the Universe 2017. Thank you. I heard that, Leeds. All right, I guess we have time for a Q&A for 8 minutes.
Okay, we have 8 minutes. Do you guys have any questions? Anyone thoughts about?
How did we start on India?
Yes, sir.
We are in a while.
So please, anyone thoughts about?
I bamboozled you?
Come on, don't hesitate. If you have any questions, he is ready or not ready.
Hello.
No, I got a question in India.
Can you hear me? Hello.
I can't hear you in India if you're talking.
Be loud, be loud.
Say something.
Hello. Can you hear me?
Be a bit loud.
Hello. Sir, can you hear me? So, in one of the slides, you mentioned that the universe is both homogeneous and isotropic. So, I'm having difficulty visualizing the isotropic nature in a flat universe. So, can you explain how it can be isotropic and as well as a flat universe?
All right, let me, I need to have clarification on the question. You're asking questions about how a flat universe and isotropy are connected? Could you
Yes.
please
Yes.
just...
Yeah.
All right, so it turns out that a universe which is flat, hyperbolic, open, or closed and spherical, they're all isotropic. If you think about a flat universe goes on in all directions equally, that's isotropic, there is no direction. A sphere has no direction. Fritz Zwicky was very famous of describing his colleagues as spherical bastards. That is, they were bastards everywhere you looked at them. That is, a sphere has no direction. And a giant hyperbola, turns out, if you think about it, it's kind of hard to visualize. It is the same everywhere you look as well. There is no specific spot on a hyperbola, a multidimensional hyperbola. So all of them are isotropic, and the homogeneity is something that we just see in the universe, that we can see in the cosmic microwave background. Okay, we have a question in Leeds, which we'll take next, and I'll repeat it for everyone, because they can't hear you. Yeah. Okay, so the question is, when using supernovae, how reliable are they as in measuring distances, because the error bars are quite large. So back in 1998, the uncertainty to a given supernova was roughly 10% in distance. Right now, with modern equipment and refinement, the uncertainty to a supernova is about 6% in distance. So it's not bad. The question is, are we sure that our distance measurements are not systematically wrong? That is, we have to assume the supernovae today are the same as the supernovae billions of years ago. And we think, to first order, we've done lots of tests. So we've looked at supernovae in old galaxies nearby and young galaxies nearby that have lots of young stars and lots of old stars. And we get very consistent answers. There are some small little effects we need to take count of now at a couple % level, but we're able to make those corrections. And so thus far, I would say they're certainly good enough to measure the acceleration of the universe, but we're beginning to get to the point where it's becoming very hard to make better measurements of the accelerating universe with supernovae, because the supernovae are beginning to potentially change over the time we're looking. And there's some other issues around dust and things I won't bore you around. All right, back to India. Okay, there's one in India.
So we know that there are various theories related to the fate of the universe. There are various theories related to the fate of the universe. So what do you think, which theory is the most appropriate regarding the fate of the universe?
All right, I'm sorry, we're going to have to, the sound quality isn't as good in India as unfortunately in Leeds. Can you repeat the question again and go a little slower?
Yeah, there are various theories regarding the fate of universe, like how universe will end. So which theory is the most appropriate and why?
All right. So the question, repeating for Leeds, is there are many theories for the end of the universe. Which is the most appropriate? So if you extrapolate the theory, just the basic theory we have right now, and we don't add anything else to the universe unexpected, then the universe gets bigger and bigger, faster and faster. Eventually, our galaxy becomes isolated from every other galaxy in the universe. Eventually, all the stars in our galaxy die, our galaxy evaporates, the black holes evaporate, and we end up in a universe where every elementary particle is separated by beyond the horizon from every other elementary particle. This is in 10 to the 100 years in the future plus. Okay? So that's the basic theory. But if anything happens in the future we don't know about, and I can't tell you that will not happen, then that can change. It is very difficult to predict the future unless you are omniscient. That is, God alone can predict the future of the universe accurately. And we can extrapolate and make informed guesses, but we will never know for sure unless we know everything about the universe. We'll take one more question from Leeds, and then I'm afraid I'm going to have to leave. Okay, so the question is, how are we experimentally going to figure out what dark matter and dark energy are? So, if dark matter is an undiscovered particle, then hopefully, if it interacts via the weak force, we will be able to uncover it when it interacts with big vats of xenon liquid that we are putting in mines. And when it interacts with xenon, very rarely, it will create a photon which we can measure, and we'll say dark matter. The experiments we've done thus far with 300 kilograms of liquid xenon have shown 2 plus or minus 3 interactions the last time I looked. There's probably a little bit better data now. We haven't seen it. We should be able to scale up these experiments by a factor of 1,000. And if we don't find anything by then, it turns out that neutrinos start interacting with the xenon, and we get into trouble. That we won't have an obvious way to find it. But I remain hopeful that dark matter will be discovered via this technique or something like it. If dark matter only interacts by gravity, then we're screwed. I don't know how we're going to ever find it, because it's just that the only way it interacts is the way we measure with gravity. So that could be a problem. So let's hope it's not that way. Let's hope it interacts like a neutrino via the weak force, and we'll find it. Dark energy, I have no idea. The only way we know how to look at dark energy is by the effect across the entirety of the universe. Our hope is that the universe will be shown not to be expanding exactly as the cosmological constant says, and that will give us an insight to why the cosmological constant is wrong. Unfortunately, at this point, the cosmological constant has been shown to be right every way we looked at it. So the way that I think we would understand the cosmological constant, if that really persists, is that that will emerge out of string theory, or the theory that brings together quantum mechanics and quantum field theory. That would be the way you say, oh, it's just naturally there in the equations. That would be the hope. No one has figured out a way to directly measure dark energy at this point. It's just so weak and so evenly dispersed, there's just no way to get a handle on it. All right? Anything else from India before we sign off? I'm sorry about our confusion on time zones. It's that time of year.
So one question.
Hello, sir. So you only talk about the expansion of the universe. Couldn't it be possible that the universe might be oscillating?
So I can't rule it out, but if the universe is going to oscillate, something else has to be going on we don't know about. Right now, the universe, as near as we can tell, is just going to get bigger and bigger.
But
So if it's going to turn around and oscillate,
that violates the
something else is
energy.
going to have to happen. Well, I can't say, but there's no reason to believe it will happen. Thank you. All right, everyone, I need to sign off. Enjoy the rest of your day. Hope to catch up with you. I will be in India in early June. Maybe I'll see some of you then. I'll be in several places, and for you guys in the UK, I'm going to be in the UK in July. So maybe I'll catch up with you then. Leeds is not on the agenda right now.